Okay, in this video I want to talk a bit more about the Jordan form. So in the previous video I talked about the Jordan form for 2x2 complex matrices and so just recall that the Jordan form, the theorem of the Jordan form for 2x2 complex matrices says that if A is a 2x2 matrix with complex entries, and I'm going to use this notation M2 of C. So this C with the bar stands for the complex numbers. So if A is a 2x2 matrix, this M sub 2 means 2x2 matrices. And this M2 of C means with complex entries, so a 2x2 matrix with complex entries. Then, and if A has a repeated eigenvalue, then there are invertible matrices P and J, which are also 2x2 matrices with complex entries, such that J is the diagonal, not the diagonal matrix, but it's this upper triangular matrix where lambda is the repeated eigenvalue, right? Like this, and A is equal to P times J times P inverse. So in terms of the similarity, A is similar to this matrix J, which is an upper triangular matrix. Okay? And we talked a bit before about finding J is easy because you just find the eigenvalue, you find the repeated eigenvalue of A, and then that's the matrix J, right? You just find lambda and then find the matrix J, and that's J. But how do you find the matrix P in the A equals PJ P inverse? Well, the idea is, so it's easy to find J. By the way, this is for a 2x2 complex matrix. For n by n, there is a Jordan form theorem, but this statement is more complicated, and it's much more complicated to find J. So in this whole discussion, we're talking about the case of n equals 2, 2x2 complex matrices. So it's easy to find J, but what about P? And the idea for finding P is the same idea for finding the P in the A equals PD P inverse if the matrix A is diagonalizable. Because A is PJ P inverse if and only if you multiply on the right, AP is equal to PJ, right? Yes, because to go from this to the equation on the right, you just multiply both sides by P on the right, and then to go from this equation to the other equation, you just multiply by P inverse on the right. So we could have stated the theorem like this instead of like this. But it's more typical to write it like this. But we can find P by using this equation. Because, okay, let's say our matrix P is this matrix. Let's say the first column is called V1 and the second column is called V2. And you have your matrix A. Okay, well, we actually don't need to label it with anything. Let's just call this A. So A times P, well, what's A times P? It's A times this matrix where the columns are V1 and V2. And recall that when you have a matrix times another matrix, you multiply the matrix on the left by the columns on the right. So A times this matrix is going to be the matrix whose first column is A times V1 and whose second column is A times V2. Now what happens, so that's AP, and AP is equal to PJ. So what's PJ? Well, PJ, P is this matrix where the first column is the V1, the second column is V2, and then J is this matrix lambda, 0, 1 lambda, right? Now what do you get when you multiply those two matrices together? Well, now we can use the fact that when you're multiplying a matrix by another matrix, again, it's this matrix, the first column of the result is going to be this matrix times this first column. And what do you get when you multiply a matrix by a vector? Remember, that vector gives you the coefficients of the linear combinations of the columns that you're taking. So this matrix P times the vector lambda 0 is going to be lambda times V1 plus 0 V2. Okay, that's the first column of the product. And then the second column is going to be what? It's going to be 1 V1 plus lambda V2, right? And so therefore, this matrix is the matrix whose first column is lambda V1. Okay, so just, and I just want to remind you that I'm using these symbols to indicate that, you know, this is a column, right? So lambda V1 is the first column, and then the second column is V1 plus lambda V2. Well, these two matrices are the same, right? This matrix is the same as that matrix. And so, in particular, their columns are the same, and so what does that tell you about the V1 and V2? If you set the first columns equal to each other, you get A times V1 is lambda times V1. And then the second columns being equal means that A times V2 is V1 plus lambda V2. Okay, let's just put a box around it to indicate that this is true. And conversely, if you have this, if you find V1 and V2 that make these two equations come true, then you can just put those V1 and V2 into your matrix P. So what you want to do is you want to find V1 and V2 such that these two equations hold. And that will give you the V1 and V2. That gives you the matrix P. So let's do an example. Okay. Let's find the P and J for the matrix A equals, okay, what's the matrix? The first column is 2, -1, and the second column is 1, 4. So what we want to do is find P and J, where J is in Jordan form and A is equal to PJ P inverse. Right. All right, well, the first thing we want to do is find J. So to find J, we need to find the eigenvalue of A. And we need the characteristic polynomial. So recall that for a 2 by 2 matrix, the characteristic polynomial is lambda squared minus the trace, so that's 6, and then times lambda, plus the determinant, which is going to be 8 minus -1, which is 9. So that's the characteristic polynomial of A. And this factors as lambda minus 3 in parentheses squared, and so therefore we have a repeated eigenvalue, lambda equals 2. No, not lambda equals 2, lambda equals 3. Lambda equals 3. And so what's our matrix J going to be? It's going to be the 2 by 2 matrix, the 3 is on the diagonal, 1 on the upper right, and a 0 down below. So that's J. And now to find P, we can use the equations above, right? A times V1 is lambda V1. In particular, V1, right? V1 is just an eigenvector with eigenvalue lambda. So in this case, we want to find an eigenvector with eigenvalue 3, and we know how to do that. A minus 3i is going to be, okay, you subtract 3 on the diagonal, right? So it's negative 1, 1, negative 1, 1. And so therefore, what's an eigenvector? Right off the bat, I'm trying to find a vector in the null space of this matrix, and I can see that 1, 1 is going to work, right? If I multiply this matrix by 1, 1, then I get 0, 0. And again, you can also scale V1 by any non-zero scalar. Okay, but 1, 1 is the simplest. So that could be the first column of P. Now we need to find V2. Well, for V2, we need to go back to the second equation. A V2 is V1 plus lambda V2. Well, actually, this equation can be rewritten to make it a little simpler as A minus lambda I V2 equals V1. Right? Those two are equivalent, just written a different way. And we can find A minus lambda I. We actually found A minus lambda I. It's this matrix. And so we said that matrix times V2 is equal to V1, and then we solve for V2. So you're going to get, so the equation is A minus 3i times V2 is V1. What does that end up being? Negative 1. Okay, this matrix times V2. Let's just call these components x1, x2. So, is equal to V1, which is 1, 1. And now can you figure out what a possibility for V2 is? Well, there's lots of different possibilities, right? But it seems like the easiest one is 0, 1. Or you could do 1, 2, or 2, 3, right? Those all work. And so, but this is one possibility for V2. And so therefore our matrix P, remember that's the matrix with columns V1 and V2. We can make P to be 1, 1, 0, 1. And so therefore, that's our P and we found our J. So A, which is, the first column is 2, negative 1, the second column is 1, 4, is a product of P, which is the first column is 1, 1, the second column is 0, 1, J, which is the first column is 3, 0, 1, 3, and then whatever P inverse is. Okay? So that's how to find the decomposition of any 2 by 2 complex matrix using the Jordan form. Let's go back and do another example using the rotation matrix. So let's say that A is, the matrix is first column is 0, 1, and then the second column is negative 1, 0. Recall that this is the matrix that rotates the xy plane by 90 degrees counterclockwise, and that obviously has no real eigenvectors. Because when you rotate by 90 degrees, you don't scale anything. But it does have complex eigenvalues and complex eigenvectors. Oh wait, this matrix is diagonalizable. So in fact, our J is just going to be a diagonal matrix. Okay, well maybe this is not the most interesting example, but let's just finish this example. I don't remember if I did this in a previous video. Actually, I probably did. But anyway, our characteristic polynomial is going to be lambda squared plus 1. And so our eigenvalues are negative I and I. And so our matrix J is going to be this matrix. Of course, you can rearrange the order. And P is going to be, see J in this case, it has something called 2 Jordan blocks. So this would be the first Jordan block, just a diagonal matrix, a 1x1 diagonal matrix, and another diagonal matrix with a different number. So this would actually be something, a matrix J, which is consisting of 2 Jordan blocks. Okay, but I didn't define what a Jordan block is. But if you read the statement of the Jordan form and you read about Jordan blocks, you'll see that this matrix has 2 Jordan blocks. Anyway, so that's J, and then what's P? Well, since J is diagonal, P is going to consist of complex eigenvectors. So we have A times V1 is I times V1, A times V2 is negative I times V2, A minus, so let's look at the first equation, that's A minus I, V1 is 0, 0, well A minus I is going to be negative I, negative 1, 1, negative I. Okay, so this times, say x1, x2, that's the vector v1, is going to be 0, 0. And now we see we can take x1 to be, I think we can take x1 to be I, and then x2 to be 1. Is that okay? Let's see. The second equation is definitely true. And then the first equation, negative I times I is it's positive 1, and then plus negative 1 times 1 is, 0. So so our V1 can be this matrix I1, and then our matrix V2, our vector V2, so that's, you have A plus I times V2 is 0, 0. A plus I is going to be I negative 1, positive 1 I. Right? So that times V2, let's just call those components x3, x4 is 0, 0. So that's our V2, and then we can get x3 is equal to I, x4 is equal to negative 1. Yes, and so our V2 is going to be I, negative 1, and so therefore our matrix A decomposes over the complex numbers. So here's V1, here's V2, is that, and then J is I, negative I, and then whatever the inverse is of this. So that's how to decompose, that's how to diagonalize the matrix A over the complex numbers. But here you have 2 distinct eigenvalues, so this is just a regular diagonalization, right? A is diagonalizable over C, but in the previous example, since you had a repeated eigenvalue, this matrix was not diagonalizable over C, and so the rest you can do is write it in this Jordan form. Well, that's the Jordan form, that's J, and then that's our matrix P, and A decomposes into P times J times P inverse. So that's all there is. That's the full story of 2x2 complex matrices and diagonalization. Okay, and this actually has applications to the trace of a complex matrix, and we'll talk about that in a later video. Thanks.